a cylinder that encloses a certain amount of charge inside this ring. Is that reasonable?
Doesn't seem like the thing I would leave to work,
Why not?
just because it doesn't.
Well, it's flat. This has cylindrical symmetry itself. If we set up the symmetry this way, as long as we stay close to the center, we can argue that the cross terms, again, will cancel out. And the only actual field that we'll have to deal with, since we're near the center, is going to be along.
My point's not to argue with it, my point's.
Oh, no, I'm just trying to say this is my justification for it. And again, these are not intuitive. They're only intuitive after you've seen them. Otherwise, you try different shapes and then figure out, okay, which one makes the most sense. So, now oftentimes we call this type of a shape a Gaussian pillbox. Look, I was going to pull up a picture of what the guy looked like. You ever seen, like, what was it, like Dickens, you know, always the bad guy in Dickens, like Ebenezer Scrooge, you know, it's kind of always got like this, these balding, got the little point noses.
Usually some kind of great big.
And big, yes, and big chops. That's Gauss. When he was 20. You're not able to picture it. I mean, really, this guy not normal. These are not normal people back then. Now more normal people do this stuff. This was not normal back then. So you always have to kind of keep that in context, right? To be educated, you have to be rich. To not be surrounded by a harem giving you a massage while you're eating grapes because you're rich, and you pick this as your fundamental endeavor in life, you ain't normal. Right? That's all there is to it. So you got to kind of take everything in context, which is the reason for the papers that we're reviewing, because these are not normal people. The way they thought was not normal. It's nice for us to look backwards and describe these. These are not normal people. Okay, so if we were to pick a surface like this, then we really have the shaft. So if I were to just draw the surface. Now, I'm going to be a little bit clever because it's helpful. I'm going to put the one edge of this thing ever so slightly inside the conductor. That's conductor. Not so far that it crosses the other side, but just enough that we can take advantage of a feature of conductors. Do you remember what that feature of conductors is? What's an electric field inside a conductor when all the charge is stabilized?
Zero.
Zero. This space has zero flux. It's kind of convenient, right? Because all the charge is out here or here. In this region in here, there's no electric field. Again, that's cheating. I know it's cheating. It works, but it's cheating. Okay, so that's what I'm doing to make my life easier. So I've got 1, 2, and then I've got this third surface, which is ever so slightly inside the conductor. 1, 2, and then in here is 3. So, play Gauss's law, it's a pretty simple game to play. The total flux would be the flux through surface 1, plus the flux through surface 2, plus the flux through surface 3, and immediately I'm going to exclude that one because I'm going to sit in a region where I don't have to deal with it. Show game. Okay, so let's look at region 1. As long as I'm in close, for all practical purposes, the field is all pointing outward, this way. Because the side terms cancel by symmetry. I'm near the center, I'm concentric, and I'm close enough in that I can ignore the other stuff. Is that reasonable? Again, it's cheating, I know it's cheating. So there's E, and it's at a 90-degree angle. So on one hand, we have E1 dA. And I always start by just assuming I have to evaluate this integral, and hopefully in most cases I don't. Plus E2. And if we make the assumption again that we're close enough in that all the field is along the shaft and none of it's in the shaft, none of it's crossing through the shaft, cosine of the angle is always going to be 90 degrees, as long as I've got a nice symmetric straight shaft, 0 flux. I mean, I have to deal with that. This is what I'm left with. I only have one surface to have to deal with, actually. That's cheating. I know it's cheating, but it works. And this is then equal to Q enclosed over epsilon. So, if the area is relatively small and we're relatively close, then this reduces to E1, A1, because E is constant. Cosine is 1. This is equal to Q enclosed over epsilon naught. So what's E then, based on this? What's A1, what's E? That's a bit of a trivial calculation, maybe, hopefully.
What do you ask?
What is E? So E1,
So it's Q enclosed over I squared epsilon.
or Q enclosed would be what? Well, it would be half of Q total divided by the surface area. Well, we could say it's over the whole area, or it's half of Q total over the round area. Because we don't have anything along the rim, and if you've got Q spaced out equally on both sides, then half of it's going to be on either side. So the uniform density is just going to be half of the total over that one surface area, just to make life easy. So we've got this times the actual area of concern. Oh no, this is not A1, this is area on the left. Right? There's two different areas. There's Q total over the whole area, and then there's a little region I'm looking at, and that's all I'm concerned with.
And we should be looking at a ratio of the 2.
Yeah. And so we have then pi r squared. Did I use r? I didn't even give that thing an r, did I? We got to deal with this. We have ambiguous terminology here. Here's the whole surface area. This thing has an r distance, but we're only looking at a portion of it. We're only looking at this region here. So we got to define them separately, but I don't want to call it r if I can help it, because normally we've been calling r the separation distance. Yeah? So we get, I mean, it's just, we got too many R's going on here now. So maybe we call this R naught and this R, just so we know that this is the R of our Gaussian surface, maybe RG, and this is R naught for the whole disk. Just want to keep them straight, that's all. There's no, so this is RG, this is a Gaussian surface disk. It's a surface area of concern. Okay. This is R Gauss. There's R disk. And then what are we missing? We're missing epsilon. Hopefully everything's in there. This is your charge density, your charge surface area charge density.
Doesn't the pi r squared?
And then we have to
cancel out?
take, and we have to deal with this too. I left one thing out, that's why I wanted to. Yeah, that's the overview. Is that, if it's confusing how it's looking, let me change colors just so you can see where the pieces are. Okay. So you have to go home and look at this in your notes.
You need that bottom pi r squared.
Let's call this Q enclosed. We'll deal with that. So this, we could write Q enclosed as Q total divided by the area divided by 2. There has to be that 2 in there because it's only the one face. So this is the area of the whole face, if you will, times pi times the radius of our little Gaussian disk. So I'll use green to indicate this is all just related to Q enclosed. Is that helpful?
Okay.
So you can see Q enclosed over the Gaussian radius squared is equal to Q total over the total area of the disk, if you will, pi r disk, what I call it, R naught squared. The same discussion we had before, so I just want to, only it's not linear now, it's surface area charge density. And sometimes we call this sigma. There's all these simplifications that are sometimes helpful, sometimes doing them makes it look simpler, but the intuition kind of goes sideways, and that's the other problem with it. Always dealing with the two dichotomies. Okay, so to this end then, I'm going to replace this all in one fashion. I'm going to say it's Q total over 2 pi r naught squared. I don't know why I'm going in and back out, I'm going to have dealing with it anyway. These terms cancel out, and I've got an epsilon naught on the bottom. In which case this just reduces to sigma over epsilon naught, everything's a constant. So the electric field is actually constant around this disk. As long as we're away from the edges and we stay near the center here, and I can actually move around a little bit, I'm not going to try to justify that, but as long as we measure this disk from the center and just stay this way kind of close, the electric field is constant for a distance, for a relatively significant distance away. That's completely different than if you have a line of charge or a ring of charge.
What you're saying? Moving this way, you're saying it's what?
And the same would be true on the other side. So within a certain region here, E is just E. It's a constant value. You get far enough away, it starts looking like a point charge, right? Yeah, out here, it's true, it does. It starts looking like a point charge. But as long as you stay in a region X that is small relatively small, I don't know what that is, you have to calculate it. Relatively small compared to R. The field is actually a constant quantity. So you can see the way these electric fields add up totally depends on how the charges are spread out, and therefore what it looks like. Now, if you tried to calculate this, you could certainly do so with Coulomb's law. How might we do it? Right, let's think about every possible thing we might do. How might we do that? Make it into a ring of some length r as you vary it from 0 to the maximum r. Right? Solve for the charge for the electric field due to one tiny little ring, and then do that for every ring until you get to the whole disk. And then you get an electric field as a function of, basically it's what we did with the line of charge, only bend the line of charge in a circle. But now each dq would be related to whatever the charge density is, sigma, times every little segment of this thing, which would be r d phi, if you will, as you go in a circle, dr. We could solve this thing. Okay? It's actually, this is the problem that was example on page 243. That is this example, so I'm not going to redo that one. Point being, we can solve this and then add up all the concentric rings over the whole disk and get the answer. I should be done now. Actually, I should, but I won't. In fact, I think I even calculated for a disk. I guess that's 22.5. I'm not going to do that. But what I do want you to think about is, let's think about. Yes.
Should this be sigma over 2 epsilon now? I've been just kind of trying to work
Yes,
this a little
yes,
bit.
yes. Well, I don't know, should it?
Well, I think so.
Yeah, why are the two faces of irrelevant again?
Where?
There's the two surface areas, the Q total over two, when you switch to green. Right, just like right there.
Oh, because if on one side you've got Q total over 2. And on the other face, you have the rest of the charge. And so if you've got a pi r squared, Q total over pi r squared. So is there
But it doesn't come into play when you have signals there yet.
Thank you. Does come into play.
So then, yeah.
Or the tubes cancel out.
Sorry, what?
The 2, when you relate it to the sigma, the 2 goes away. The 2's part of the sigma, so you don't get a sigma over 2. Is that right?
I just made a simple substitution from all the way left. You have E1 equals Q enclosed over epsilon pi r g squared. And if that thing is equal to that over there, with the exception of the epsilon not in the denominator, then all you have to do is move that epsilon not over.
This one? And this one?
No, I see now that you have the 2 up there in your green, it makes sense. It's just sigma over epsilon not.
Yeah. The trick, I'm going to emphasize something, when you've got a flat conductor, you've got charge on both sides. It's not just one layer of charge, it's actually charge on both sides.
I'm just slowly catching up with all this algebra as you're going, so I'm always kind of 2 steps behind you trying
Okay.
to adjust.
Well, and I'm glad you did, because that, what was missing in part was because I left out that 2 up at the top. Now, here's where it kind of gets, well, I got a couple minutes to think about this. But here's, I don't want to use this part here. But here's what I want you to think about now. If we were to put another disk over here with the same amount of negative charge, let's call it negative Q total, and put it kind of close to this thing, some distance, some small distance across. Maybe we call it D just to. Let's get rid of this stuff for just a second. Same charge over here, and we bring another charge in over here. First of all, what happens to the charge in the presence of the negative charge as we bring this in?
Does it all go to one side?
It all goes to one side, it's a conductor.
Right.
So the problem changes, or at least the charge movement changes, if we bring a negative charge closer because of the induced movement of the electrical charge. So my question then is, what is the electric field here when that guy's in? So, so let's make D small with respect to the radius of this disk. There's your still same R naughts. Okay, they have the same. Dimensions are now equal, but we have 2 of them. One's negative, one's positive. We got plus Q, minus Q. We just bring them close together. Call that a capacitor, by the way, a charge
Are
capacitor.
they like this or like this?
Oh no, they're flat.
Okay.
Oh God, you want to do
Okay.
that?
I wasn't-
It'd be a dipole at some point, I guess. If they, well, no, I don't want to go there. That's nasty. That would not be nice. Okay? So all the charge in this space is also going to pull inward like that, right? Is that conceptually what's going to happen here?
Both are conductors then.
Yeah. Nothing strange. I'm not trying to use a sleight of hand here per se. If we use the same Gaussian cylinder, what would E be here?
Would it be 4 times stronger?
Solve it. I'm going to put a Gaussian cylinder in here, just inside here. I'm not going to enclose this. I don't have to enclose this. I'm just going to enclose this over here with some little radius RG. Make this length some value. Got a little smaller. Solve Gauss's law for it. It's the same problem as previous, other than the charges have moved around. So what does it look like?
Well,
What happens to the charge density?
it doubles. That 2 just, what we were just talking about, just goes away.
So solve it. Come up with an answer before we go. You can. And I'll put it over here as well. Okay. None of this stuff changes, except for this one.
Why are you squaring pi?
Oh,
Yeah. It's just now, sigma is just a different sigma, but it's still the same.
yeah, this sigma is twice sigma when you only have the one from the previous problem. Or sigma with no negative plane nearby.
Would the other disk generate an electric field at that point as well, though? Would that count? No?
In a way it does, but in a way it doesn't.
I feel like if the negative one was there, it would still have an electric field going that way, and since they're vectors
It's-
combined, I don't think they would count.
But the reason it's there is because it's being attracted, or the presence of it there pulls all the rest of the other charge over. And so it's actually a sliding scale. It's not quite the same problem because the charge is no longer all distributed in the same place. The equivalent of it is essentially the same thing as having half the charge here and half of it here, and then having this charge pull back against it.
Okay. So, like, if that was a non-conductor and everything stayed on one side?
If
And when you would
if
add
it all
with
stayed
them
on
as
one
well?
side, or if you only looked at the charge density here, then it's basically you've got more charge. How else to say that? I had to come up with better words for that. I'm not going to say, I know I'm going to say it awkwardly.
So whether or not they're conductors or insulators, your E is gonna be the same anywhere between them.
So, coming back to a question related to accelerating electric charge and electric force from chapter 21. How can you have a charge in an electric field, in a constant electric field, you calculate the force? When does that happen? Well, one way it happens if you get an electric charge inside two faces of a capacitor. And that electric charge will accelerate based on the direction of the electric field. And that acceleration will be uniform and constant within that field, because the field itself is a constant value.
So that's how they do like the printing example in the textbook? So that's a constant, like anywhere in there, that field will be the same?
Yeah, so if you could take two charge plates and put a tiny little hole so that you could get charge inside, then once that charge is inside, you shoot electrons in there somehow. A television set is another example. You get the charge inside, it's then going to accelerate through from one side to the other and gain kinetic energy due to that process. It's going to come out excited. So it looks like a uniform gravitational field in that case.
That's what particle accelerator is, or?
Oh, much more complicated than particle accelerator. So. In that case, it's a series of magnetic
Right. And it's gotta somehow keep something very, very small in exactly the right place while it's moving very, very fast.
In an electric field to accelerate.
Is there a test on Thursday?
Thursday.
Yes,
Well, it's counterintuitive, and that's a bit of the problem with it, is that it doesn't.
It's really counterintuitive. I'm like, yeah.
It doesn't seem like this would go away anymore, because it's just inside the conductor, which by the properties of the conductor would normally make it all zero, but that's the first thing inside there. So we'll be able to back it, because it's on the other side of the chart.
I see a cue. Oh yeah, you wanna go grab smoke?